All right, so in this video, we're going to walk through how we can construct a confidence interval for a proportion using what's called a scored confidence interval. So the example here is there was a poll done recently by ABC News where they asked people if they had gone outside the previous week, and if so, had they worn a face covering to per the recommendations to help mitigate the spread of coronavirus. So here, let's let random variable x denote the number of people out of a random sample of 443 adults in the US that said they did wear a face covering in the past week. So for the ABC News survey, 443 people in their survey said they had left the house in the previous week. And based on that, they then asked these 443 people if they had worn a face mask or not. So that's where this 443 comes from. So we know how many people are in our sample, but what we don't know is the proportion of all people in the US, all adults in the US that said they had worn a face covering in the previous week. So the P is unknown. But we've got our sample, and from our sample, if you recall, we found that 55% of the sample did wear a face covering in the previous week. So that sample proportion we've shown in general, this is an unbiased estimator. So that would be a good place to start. But of course, we don't know how much off p hat is from the actual value of p. So we know it should be close, but for different samples, we're going to get slightly different values for p hat. So how can we factor that into our sample, into our estimate? So we've done bootstrapping to kind of estimate the variability from the sampling process. We've also talked about the central limit theorem for a proportion. So if you recall, for a proportion, the central limit theorem says that the distribution of sample proportions, are going to be centered at the value of the population parameter. So the expected value of p hat is the population proportion. That's why it's unbiased. And we also have shown what the variance of p hat is, and from that we can find the standard error for the sampling distribution. So if we knew what p was, we could find out in theory exactly what the sampling distribution should look like. So this is going to be our starting point for what we're going to call a scored confidence interval. So because this distribution for the sample proportion is normal, we therefore could take a look at the z-score for each sample proportion. So recall, for each sample proportion p hat, I can calculate how far away is that from the value of p, and then divide that by the standard error, and that's going to standardize that. It's going to tell me how many standard errors p hat is from the population proportion p. And since this is a normal distribution, we know that between a z-score of minus 1.96 up to 1.96, the middle 95% sits. So this is like the empirical rule that says between about 2 standard deviations below and above the mean sits about 95% of the values. So let's isolate one side of this inequality, say this part over here. Now, if you think about that equation, p is the only unknown in this equation. We know what p hat is, namely, we know that p hat was this 0.55, so we can fill that part in. And we also know what the value of n is. We know that there were 443 people in the original sample. And so the only unknown I'm going to highlight in green are these values for p. So here we've got an equation with one unknown, and so you could solve this for p. So for example, I could multiply both sides by the square root of p times 1 minus p over 443, and then square both sides and group my p terms, and what you'll get in the end is a quadratic expression for p that you can solve. And solving this equation for p gives us a value of 0.503. So don't even bother trying to do the algebra yourself. You can kind of just trust me on this. But if you really want to practice some algebra, you could verify this. And similarly, we could go ahead and take a look at the other equation, which is finding the upper limit for this confidence interval. So what value of p is going to give a p hat value that would have a z-score, that would make our p hat value of 0.55 have a z-score of 1.96. And so solving that equation would give us an upper limit of 0.596. So here we found lower and upper limits for the value of p that would make our sample proportion 0.55 have a z-score of either 1.96 or negative 1.96 or a positive 1.96. And those values of p we can set as our upper and lower cutoffs for our confidence interval. And so one thing I just want to mention is that this process works only if we can use the central limit theorem to describe the distribution of sample proportions. And for small values of n, this is not going to be, the normal distribution is not going to be a good estimate. So the rule of thumb for determining what is large enough is given on the bottom, right? So we want to make sure that n times p is bigger than or equal to 10, and we want to make sure that n times 1 minus p is bigger than or equal to 10. That certainly is true for this example where we have a sample of 443 adults. So this is, in theory, how the scored confidence intervals work. And on the next slide, I'm going to show you what those solutions look like in general and how we can use R to find these calculations for us.